Okay. So I kind of put these two things together. We're going to start talking about now a quantity called electric flux. And the idea of flux is a very important concept in science and engineering. And first of all, I made a kind of a qualitative description of flux. So imagine that this room were a river. And the ceiling here represents the surface of the water, the floor represents the bottom of the river, and the water's moving in this direction. Now, if the water were moving in a nice uniform way, if I picked a point in space, that point, the water's moving past it at a certain speed, so we can represent that with a velocity vector. And imagine that the velocity is the same everywhere, up and down. So you could represent that with a bunch of vectors. Now imagine something like this hoop. Right here. Okay. If I orient the hoop like this, there is water going through it. There would be water going through it now. And that's related to a quantity called mass flux. When you have water going through this, right, that's what the flux is basically. The flux would kind of represent how fast the mass is going through this hoop. Now let's talk about the different variables involved here. One, if I were to rotate the hoop like this, how much mass would effectively be going through it? Right? About 0, give or take. So this quantity called flux is dependent on this angle here. The flux is a maximum at this orientation. What's the other way I could, in this example, if I could snap my fingers, change any variable I wanted to, what's another way I could affect the flux through this hoop?
Radius?
Yeah, I could make this hoop larger if I could. That would affect it. And what else?
If it's rotating.
Okay, let's leave this alone. There's one that doesn't have anything to do with this. The speed of the water. So the mass flux describes something about how much mass is going through this hoop. And it can be affected 3 ways. Orientation, make this thing bigger, or the velocity, speeding up the water. Okay. So in a similar sense here, there is a quantity called electric flux. I'll start with kind of an algebraic description of it. Let's say I've got some sort of area here. Does not matter what shape it is. And let's say that I've got an electric field vector here that's going through it. Okay. The flux, the electric flux, would equal the field strength. I'm going to put magnitude of the electric field times the area of this geometry, whatever it is. Now in this example, I'm assuming this makes a right angle here. We're going to get more specific in a minute. And I'm assuming that this field does not vary along this area. Right? So what would the units on this thing be? Flux. Electric flux, what would its units be?
Units per coulomb per unit area?
Yeah, well, I think I heard it. Newton per coulomb meter squared. Now I've got to talk a little bit about what it's related to. Electric fields can be described by what are called electric field lines. Let me look at a point charge for a moment. Consider a point charge here. Electric field lines are always tangent to the electric field vectors. Let me draw them in here and then I'll talk about the properties. The electric field lines around a point charge look like this. Right? They have a direction, they're outward. They're not vectors though, they're just lines that help us visualize the fields. Here are the rules for electric field lines. 1, the electric field lines tell you about relative strength. The magnitude of the electric field is directly proportional to the number of lines. Technically, it's per unit volume. However, sometimes for the sake of visualization, let's just look at it on a per area basis. Technically, it's the number of field lines per unit volume, honestly. But it's hard to draw that on a two-dimensional page. So, let me draw a few more field lines here. Hold on. Let me get this example done. Boom, boom, boom.